Well, good morning. This is 11 o'clock on Thursday, the 21st of September, 2017. Should be linear algebra class. Right now, I'm the only one in the room, but I'll go on and get started from here. No major announcements that I know about. The sort of a minor one is that on most Fridays, I'm on the Birmingham campus nominally from 7:45 to 11:45. Now, most Fridays, usually get there a little before 7:45, though if I've got bad traffic at UAB or something, it may be a little later. And most times I don't leave right at 11:45, but sometime after that. However, Friday, tomorrow, we have a meeting that they schedule for 12:30, of course. So that means I won't be leaving anywhere close to 11:45. I'll be in the office until 12:15, 12:20, 12:25, something like that, before I have to go to the meeting at 12:30 in another building. So I will be longer office hours than normal, not by a lot, 30 to 45 minutes longer, but than what I normally am there. And then I'll be at the meeting and probably leave from the meeting to go home from there. So I won't probably be going back to the office unless I've forgotten something or something like that. So anyway, that's the only minor announcement. Now, the other one that I've been talking about all week, and last week too, was the fact that the Vice President has said that the unpaid students were to have been removed from the rolls as of last evening. I don't know if it happened. I haven't seen check the rolls yet or not. But if it hasn't happened, please complete payment as soon as possible. If you were removed from the roll and want to stay with the course, please get that payment done as soon as possible. They usually will let you back into the course. Can't guarantee it, but you can give it a shot anyway. Don't want to lose you, so I hope you get it done. All right, that's all I can think of right now. Let's move on to where we left off last time. Last time we were at the bottom of page 46, Chapter 2, Matrices, 2.1, Operations with Matrices, and we were talking about linear combinations of column vectors. We had done that in the partition matrices above, and this is just a little blurb. It's the stuff we were doing before, just making a thing. The matrix product AX, let me get my pen set up. AX, where X is a vector, A is a matrix, is a linear combination of the column vectors A1 that we were doing before, A2 up to AN, such that it's X1 times the column vector A11, A21, A31, ... down to AN1, M1, plus X sub 2 times the column vector A 1, 2. Good deal. Glad you're here. I get tired of talking to myself. All right. Now, have you heard anything from Kimmel? Okay. Well, I think it's something later. So hopefully you'll be here too. What's that?
I haven't seen him since last time.
Right. Sometimes I press that button, nothing happens, but it looks like it's working this time. Hope so anyway. We're starting on page 46, bottom of the page, linear combination of column matrices, which we did this thing before, but we didn't name it this. Okay, this is in that box at the bottom of the page. X2 times A22, A32, dot, 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 down to AM2 plus X of 3, the variable X of 3, times the column vector A13, A23, A33, dot, 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 down to AM3, plus, dot, 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 plus, yuck. I'm sorry. X sub n times A1n, A2n, A3n, dot, 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 down to AMN. Okay. That is our, okay. What we called this before, these are the column vectors represented by the component entries of your column entries of your matrix A. Okay. If you look at just the column entries, which we call the column vectors of them, your first variable x of 1 multiplied by each of those, the second variable by each of the second column, third and third column, all the way across to the nth column. Okay? That's called a linear combination of these column vectors. So you're multiplying a different variable by the linear combination of all those. That gives you your full system of equations. Now, furthermore, the system AX is equal to B, AX equal B, where B is also a column vector, is consistent if and only if that B, vector B, can be expressed in such a linear combinations where the coefficients of the linear combinations are a solution of the system. Okay, where the coefficients of the linear combination, the x1, x2, x3, x up to x of n, where they are a solution to the system. Okay. Now, remember what consistent means? The system has at least one solution. Doesn't have to have tons of solution, at least one. It can have an infinite number of solutions, okay? So it doesn't have to have just one, okay? But to be consistent, it has to have at least one. Okay. That was the bottom of page 46. We're right now moving to the top of 47, which is going to be a new slide too. A new clean page here. Example 7, solving a system of linear equations. So here's the system of linear equations. X of 1 plus 2x2 plus 3x3 is equal to 0. Second equation, 4x1 plus 5x2 plus 6x3 is equal to 3. 7x1 plus 8x2, that's an ugly 8, okay, plus 9x3 is equal to 6, okay? Now, that's a linear system, a system of 3 equations, 3 unknowns. Writing that as a in the matrix equation, AX equal B, okay? You could write the entire coefficient matrix times the x1, x2, x3 as a column vector, and the B is a column vector 0, 6, 3. That's how we normally do. But how they're writing it this time is like how we just did. X1 times the first column of coefficients, 1, 4, 7, plus x2 times the second column of coefficients, 2, 5, 8, plus x3 times 3, 6, 9, and that's equal to the column vector 0, 6, 0, 3, 6. Okay. Sorry about getting cramped in the page. Now, why they wrote it like that, I'm not absolutely certain. I think it's going to show up in a minute. Okay? But they said using Gaussian elimination, you don't usually use Gaussian elimination in that form. You do it in our standard form, which I think is what they intended to do. They just didn't write it that way. And that would be do 1, 2, 3, 0, 4, 5, 6, 3, 7, 8, 9, 6. Okay? And let's do our Gaussian elimination. Now notice they didn't say Gauss-Jordan, they say Gaussian, which means do a row reduction, that you do it into row echelon form and not reduced row echelon form. That means we will do back substitution if we need to. All right, what would be your first step to do that, to solve that using Gaussian elimination?
Make sure the first number in the first row.
And thank goodness it is. Okay, next step. The second row will have to be a 0. Yeah. How do we get that 4 to become a 0? Negative 4, row 1, plus row 2. Okay? So let's do that step. Now we're using the first row, so we write it down. 1, 2, 3, 0. Sorry about my throat. I don't know what the problem is. Okay, next, do that step. 0, negative 3, negative 6, 3. Okay. Now what's the next step? How do you do that? Negative 7 times row 1 plus row 3. Okay, and do that, and what do you get? 0. Is what? Negative 6. Got it? Second. Negative 7 times 3 is negative 21, plus 9 is what? Okay. You do what you said here. Negative 7 times row 1, you got that part. So it's negative 7 times 3 is negative 21, plus row 3. So negative 21 plus 9 is negative 12. All right. And then the last entry is 6. Okay. All right. Now, what next? Yes, and how do you do that? Absolutely. So row 2 divided by negative 3. Okay. So, leaving the first row alone, 1, 2, 3, 0. What's the new second row?
0, 1, 2, and -1.
Okay. And then, what's the next thing we want to happen? Okay. Now, actually, the easiest way to do that is not to use this one, but to use this one. And just multiply that row 2 by -2 and add to this. That will do it for you, right? So let's do it. Otherwise, you have to multiply by -6. So you already got it here. So -2 row 2 plus row 3. Okay? What will that give you? 0, 0. Second? 0, 0. Wait, yeah. So we wound up with a row of zeros, but it's at the bottom, that's fine. And guess what? We have it already right now in row echelon form. Okay? You got the first non-zero digit in each row is a 1. Underneath those 1s are zeros, and and all the leading ones step to the right as you go down. Okay, so everything works. So what do you have to do now? Since you have a row of zeros, you're not going to be able to solve for the third entry, which is your x3. So what do? Let that be a parameter. What parameter do we want it to be? T. So let x3 equal t. Okay? Now, let's jump up one row. It's the second row, and what does it say then? x2 plus 2t, right, is equal to -1. Okay? So that implies that x2 is equal to -2t minus 1. Right? Okay? What does the top row then tell you? x1 plus 2x2 plus 3t equals 0. Okay? But we know x2 in terms of t2 also, so it would be x1 plus 2 times a -2t minus 1 plus 3t is equal to 0. Okay? Multiply that out, x1 minus (4t) minus 2 plus 3t equals 0. And for some reason, my pen is doing some really strange things here. It wrote it and then it just took it off. Okay? Now, let's combine these two, and that's going to be a minus t, right? Okay? But add it to the other side, and you have x1 is equal to t plus 2, right? Is that what you said? All right. So we have x1 equal t plus 2. My pen is so slow in writing. It's so slow in doing everything now. Okay. Even erasing a little bit. Okay. It's t plus 2. X2 is equal to minus 2t minus 1. And x3 is equal to t. Okay. Writing them all together there. Now, that's an infinite number of solutions for any t you choose. Plug it in. They chose, or I'm going to choose, one solution would be t equals 0. Then you would have 2, -1, 0. Okay? They happen to choose x3 equal -1, so t is equal to -1. So in that case, let's see. So k to do it that way, but I think it's a little faster just to write it. Okay? That ordered triplet would be when t is equal to -1, -1 plus 2 is 1. -1 times -2 would be positive 2, minus 1 is 1, and -1. Okay? And let's see if that's what they got. Yeah, 1, 1, -1. Why they chose that one, I'm not sure. Okay, so whatever t you put in there, you can come up with another solution. You could put decimal numbers, you could put irrational numbers, you could put any number you want to and come up with another solution for the whole thing. Now, because this one works, this, by the way, is 1x1, this is an x2, this is an x3, okay? All right. Now, what I'm going to do, unfortunately, I need to erase most of what's up here. All right, we did it right, so we don't need that anymore. And the pen, the eraser is so stinking slow. I think I need these. I got, goodness gracious, this is slow. Okay. Whew. All right. Therefore, you could have written this, your x1 in this case was 1 times 147 plus 1 times 258 minus 1 times 369, and supposedly that's equal to 036. Let's see if it is.
So that's how you write it when you're finished?
What's that?
That's how you write it when you're finished?
I'll find it just perfectly okay to leave it like this. I would have done an ordered triplet of t plus 2, comma, minus 2 minus t minus 1, comma, t. That would be my solution. But they picked out a couple. I picked out one, they picked out another one. But what they're trying to show you is how to write that as a linear combination. What they're saying is, if you have a solution for the set of equations, a consistent set of equations, any solution there will make this a true statement. So let's see if it does. 1 times 1 is? Plus 1 times 2 is? 3. Minus 1 times 3 is? 0. Sure enough, that's right. 1 times 4 is? Plus 1 times 5 is? Minus 1 times 6 is? 3. Got it. And 1 times 7? Plus 1 times 8? Minus 1 times 9? 6. Yep, that works. And every solution you put in, if you put in 2, negative 1, 0, 2 times 1 is 2, minus 2, that's 0, because this one was a 0 all the way. Then if you do 2 times 4 is 8, minus 5 plus 0 is 3. 14, 2 times 7 is 14, minus 8 plus 0 is 6. Yeah. Every solution that you get here, you can put in this linear combination, and you're going to make a solution. That's what the solution is.
So if they ask you to write it as a linear combination?
Yeah, that's what you do. In fact, I would just left it as x1, x2, x3. But if you wanted to plug in and check, you could do what we just did. Okay. Now, I mentioned before, we had started off talking about partitioning. Here they do a little bit more and basically don't do another thing with it for quite a while. So I'll show this, though they just say, voila, here it is, and then leave it. Okay, you all right with erasing this? Okay. What if you had a matrix? 1, 2, 0, 0. 3, 4, 0, 0. Negative 1, negative 2, 2, 1. Okay? All right, that's your matrix. You can partition that matrix any way you want to. We were partitioning by columns. You could partition by rows, or you could partition by blocks. They did a block like this and a block like that. That gives you a 2 by 2, a 2 by 2. That's a pretty easy 2 by 2. It's all 0. And then a 1 by 2 and a 1 by 2. That's a partition. Now, they're not saying what you do with it or anything else. You could just do it. If you had partitioned it by columns, okay, and your partition was like we did before, just like that, then you could represent this as, name this C1, C2, C3, and C4. And because these are technically vectors, they write them bold, I have to put that in. You could say that the matrix of C1, column vector C1, C2, column vector C2, column vector C3, column vector C4. Okay? That represents the very thing we had there. Or, if you had partitioned this by rows, okay? Then this would be row 1, that's a row vector, row 2 is a row vector, and row 3 is a row vector. And then you could have said this was partitioned as row 1, row, I can't write. Okay, try it one more time. Row 2, row 3. It just saves some writing and not any other real deal with that, but those are just other ways to express that. Now, here's a linear algebra applied at the bottom of the page. Many real-life applications of linear systems involve enormous numbers of equations and variables. For example, a flight crew scheduling problem for American Airlines required the manipulation of matrices with 837 rows and more than 12,750,000 columns. Let's not do that in class, okay? All right. That application of linear programming required that the problem be partitioned into smaller pieces and then solved on a Cray supercomputer. Okay, not even, a regular graphing calculator or regular laptop or even our system here, you needed a supercomputer. So if you want to look into that, they do give you a source there, and you can write your paper topic on it. This can't be your source, but the source they give you can be. You go to the source. All right, we finished 2-1, finally. Homework exercises, I've assigned most of these before. Either 1 or 3 or both. Any of the odds 5 through 11, 13 or 15 or both. By the way, calccheck.com has worked out solutions for all these odd number exercises. Any of the odds 17 through 29. Any of the odds 31 to 37. Do 39. Any of the odds 41 to 47. Any of the odds 49, either 49 or 51, or both. Do 53. 55. Okay. Time out. This is one of the little things that bugs me about this book. This same author wrote our Pre-Calculus Algebra, Pre-Calculus Trig book, which is one of the math is just the math, but his calccheck.com, his LarsonPrecalculus.com, now he has a CalcView.com or something like that. It's just, it has so much really good, useful stuff, okay? Ancillary stuff, you can just call in the library and work it out of that. Okay. One of the things that bugs me more about this book than about the others is that, for instance, here he introduces a concept, diagonal matrix, in the problem set. Not in the text, but in the problem set. Now, this isn't the only time. He's going to do it several times throughout the course. And here's a definition of a diagonal matrix. A square matrix, it's got to be square. It's diagonal when all the entries that are not on the main diagonal are 0. Okay? The main diagonal generally is not zeros. If they are, you don't have a very interesting matrix. But the non-main diagonal entries are all zeros. And I think, if my memory's right. All right, good deal. Good to see you. Perfect attendance today. Way to go, Tate. All right. We just finished 2.1. I was talking about exercises 57, 58. The problem is introducing the concept of a diagonal matrix, and we're just talking about what it was. All the elements on the diagonal, let me put it that way, the elements on the diagonal are not necessarily 0, and every one of the elements off the diagonal are 0. That's a diagonal matrix. Now, if you think about it very hard, none of those elements in the diagonal should be 0. They could be, like 58 shows one that is, but that's let's just leave it alone. It is, they don't have to be non-zero, but a lot of times you'll find that all the diagonal elements are non-zero, and all of the ones non-diagonal have to be zero. Okay. And then problem 59 also uses something about finding products of diagonal matrices. So do that one. 61 is a guided proof. They sort of help get you through a proof, so you can do that if you choose. You can do either 63 or 65, or both if you choose. 67 is a proof. You can do that if you'd like. Except, I've missed one. If you look at 63, 65, that is instructions. Now they introduce another new concept, the trace of a matrix. Okay? Not in the text, in the problem set. I found that less than adequate. I think if you're going to give things, give it in the regular text, not in the problems. But they give you what a trace is. It's the sum of the diagonal entries. Okay? Now, it doesn't have to be a diagonal matrix, but it does have to be, it's the sum of the diagonal entries. Okay? And they have to be trace square matrices too. So do 63 or 65. 67 uses that concept of trace to do a proof. And then the odds, you can do the odds 69 through I know 69 through and or 71. The exploration begins with 73, which is sort of interesting. You can do that if you choose. There's a proof for 75. You can do it if you choose. And then the rest of these are sort of generalized type things. 77, 79 is an applied problem. 81 is an applied problem. Then there is block multiplication in 83. Seems like to me I would almost say that's a new concept here. It kind of is what they call block multiplication. So I'll let you look at that. If you get bogged down with it, forget it. Usually if it's not in the text, I'm not going to test you over it. There may be some that are going to show up in the text later that would be qualified, but that one I don't think will. True or false, not a bad idea to look at those, just don't expect any of those on your test. All right, that finishes 2-1. Let's move on to 2-2. Sorry, my head is clogging up again, and I don't know why. May have to sneeze soon. I've got a really itchy nose. I hope I don't have to, but it may be coming. Less 2.2, or 2.1 was talking about matrices, including the properties of matrices, operations of matrices. That's what 2.1 was. Now we're going to do properties of matrix operations. Okay? So this is still continuing what we call the algebra of matrices. And here's theorem 2.1, which has 6 pieces to it. And here are those pieces. Now, both of you have books? Or is yours? Okay. So, in case you need to see these again, I will write them, but I'll write them very abbreviated form. This is theorem 2.1. Okay, properties of matrix addition and scalar multiplication. We've hit on this before. Here's the given. A, B, and C are M by M matrices. Okay. C and D, I lost my place there. C and D, capital A, B, C are matrices, M by N. C and D are just scalars, meaning just any old two numbers. Now remember, they can be whole numbers, they can be integers, they can be rational numbers, they can be real numbers. Technically, they could be complex numbers, just any two scalar numbers. With that in mind, these are true statements. First of these, matrix A plus matrix B is identically the same as matrix B plus matrix A. In other words, the addition of matrices is commutative. It doesn't matter which order you do them. Okay? It's called the commutative property of addition. And that's for matrices. All right. You know that's true for numbers. Real numbers, even complex numbers. It's true. Okay? Number 2. A plus B plus C is equal to A plus B plus C. Goodness gracious, I can hardly breathe. I don't know what it is. Maybe when the temperature heats up outside, the cool kicks in there. I don't know what. But this is the associative property of matrix addition. Okay? Number 3. This is a rather bizarre one. When you have two scalars, you multiply them together, C times D, and multiply that product by matrix A. That's the same as you get by multiplying C times the product of D times A. Okay? Now, that is one form of associative property of multiplication. It's two scalars multiplied to get by a vector equal to a scalar multiplied by a scalar vector. So you got 2 parts scalar, 1 part, matrix, and 1 part matrix. So that's a fairly weak associative property of multiplication. Very limited. Okay. Now, this one's much more general and true and useful. 1 times the matrix A is the matrix A. Okay? Now that's numerical 1, and that is the No, I'm sorry. I've got to look at my book more closely. It works for 1. My eyes are not. Okay, it is a 1. I'm pretty sure that is a 1.
For 4?
Yeah.
Yeah, that's a 1.
Okay. Now, what it also works for, if that would have been an I, okay, which is I is your identity matrix of the right size, okay, but we haven't talked about multiplying. In fact, have we even introduced identity matrix? I thought we had. I don't know. I've taught this course so many times, I can't remember what we talked about and what we haven't. But that's the number 1. Okay, that's the identity element for multiplication, which they call the multiplicative identity. Okay. Number 5. C times A plus B, some scalar, times the sum of A plus B is the same as CA plus CB. Yeah. that is a form of a distributive property of multiplication over addition. Now, I like to have a little bit more descriptive than that. It's the distributive property of a scalar times the sum of two matrices. Okay? And that's what it is. For some reason my B got super subscripted there. It shouldn't be. I was paying more attention to the book than I was where I was writing. And finally, number 6. Okay? It's another distributive property. This time, you're adding two scalars together times a matrix A. That's the same as C times A plus D times A. Okay? It is a form of a distributive property, but this one, it's gracious. I call this distributive property of a scalar over the sum of two matrices. This is distributive property of a matrix over the sum of two scalars. Okay? So, now that's not an exhaustive list of the properties, but it is a list. There's a couple more that I would see as fairly important that you could name, but they don't really add a lot to the context of it, so we'll leave those alone. Let's move on to example 1. I'm sorry. First, it clogs up. Now, my head is beginning to feel the clog, and it's just almost beginning to throb. It's aggravating. Sorry about that. Okay. Now, this has nothing specific to do with any of those properties, so you can find application of it there. We're adding a bunch of matrices, and these happen to be column matrices, which you could call column vectors. Pretty simple. 1, 2, added to, -1, -1, added to, 0, 1, added to, 2, 3, 2, -3, and add that to, no, that's equal, okay. Okay. Rather than write down what the answer is like they do, let's just calculate it. What is that equal to? Add matrices, two things have to be true. They've got to be identically the same size. Okay? All right. And then you add corresponding entry to corresponding entry. So this will be
the first one.
First, yeah, it's basically your first row. You're absolutely right.
That'd be
2. Goodness. 2. Okay. Next entry. -1. All right. Let's see if the book got that. They did. Good for them. All right. Now, we used a couple of the properties there. I did anyway. I used associative property. What I did, I associated these two together, knowing that's going to be 0, and that was left that to be 2. Now, what property that wasn't listed in the table, I said there were some others. I wouldn't go into them now, but 0 is the additive identity element. You add 0 to any matrix, a 0 matrix to any matrix, you get the same matrix you started with. Same thing with entries. If you add 0 to an entry, you get just whatever you have. And I associated it differently down here. I associated these two, knowing that was going to be 0, and all I had to do was add these two together. Okay? And -1. So you probably use some of those principles, probably not thinking, oh, this is that principle. You just used it. Okay. Now, what I was just talking about is coming up here. One important property of the addition of real numbers is that the number 0 is the additive identity element. Okay? That is, real number C added to 0 is still C. You can't change it adding 0 to it. Okay? It doesn't change it. For matrices, a similar property holds, specifically that if A is an M by N matrix, okay, and 0 is an M by N matrix, then when you add those together, you get the same matrix you had to begin with. And by the way, for a generic matrix, we usually put the M by N, row by column. For something like the 0 matrix, we don't usually put the by in it, we just put M in. And that means same thing, M rows in columns. Okay? Why they're not more consistent with the way they write it, I'm not sure. I wish they were. Okay? Later we'll see an identity matrix, which I haven't introduced yet. They're always square, so you could just call that I sub M or I sub N, meaning square matrix of that dimension. Okay? So, anyway, you're adding this one, they're same size, so you can add them. And that 0 matrix, M rows, N columns, every one of those entries has to be identically 0. Okay? So if this was 0, 2, 3, that would be the matrix of 2 rows, 0, 0, 0, and 0, 0, 0. All right? Now, when the size of a matrix is understood, you may denote the 0 matrix simply as by 0 or O. So if you write it as 0, then bold it. I can't bold, so I'll put the arrow over it. Though that usually represents vector, a 0 matrix doesn't have to be a vector. It can have multiple components. Okay. So the following properties of 0 matrix. The first table is properties of matrix addition and scalar multiplication. These are some properties of the 0 matrix. And since it'll take a little bit of room to write, I'm going to clear the screen and write from here. Oh, man. All right. Again, A is an M by N matrix. C is a scalar. Okay, then the following properties are true. All right, let's just go with it. The first of these, A, which of course is an M by N matrix, plus the 0 matrix, that is also an M by N matrix. So they don't put the by it. If you add those together, you got to get the A matrix. There's just no way around because they're the same size. All the entries in this are 0. So A11 plus 0 is A11. And every entry is added to 0. It doesn't change. Okay? Pretty trivial. Okay? Now here's another one. May not be quite as trivial. If you have the matrix A and add it to exactly its negative, then you're guaranteed to get the 0 M in power. That is called the additive inverse. the negative of a matrix is the additive inverse of the matrix. Okay? And then number 3. If CA is equal to the 0 matrix, I'll call that 0MN. Okay? If that's true, this implies that either C is equal to 0, that constant scalar C has to be 0, or that A has to be the 0 matrix. Okay? One or the other, no way around. Okay? There's no mixing of that. You can't take C to be a really small number and A be almost a 0 matrix. Not going to work. Either C0 or A0 is the 0 matrix. Okay? I think example 2 is going to use some of that. So, if I can breathe, we'll do example 2. Solve for x in this equation. 3x, and that's a capital X indicating it's more than likely a matrix, plus A is equal to B, where A is this 2 by 2 matrix, 1, negative 2, 0, 3. I don't know why this just dawned on me. Let me check that. Okay. I had checked that. Making sure of that. All right. And the B matrix is negative 3, 4, 2, 1. Okay. Got it. Now, how do we find x? There it is. From there. What would be your guess? If those were variables, it would be pretty simple, wouldn't it? And A would be a number, and B is a number, X a variable. You just solve for it. Guess what? That's what we do now too. Let's just subtract A from both sides. Okay? So 3x is going to be, let's write down what B minus A is. Okay, start with B. First element, negative 3 minus 1 is negative 4. You do the next one. Okay. Okay. We're doing B minus A. So you did minus 3 minus 1, that gave you minus 4. So now next is 6. Very good. Next. 2. Next. Second. Negative 2. All right. Now, what would you guess you would do next? Divide by 3. Or multiply that by 1/3. Okay? So your X matrix will now be what? Negative 4/3, 2, 2/3, minus 2/3. Okay. Man. All right. See what they got? Negative 4/3, 2, 2/3, negative 2/3. Very good. All right. Now let's look at some properties of matrix multiplication. Notice we did properties of matrix addition and scalar multiplication. Properties of zero matrix. Now we're going to do properties of matrix multiplication. We've already done matrix multiplication, let's look at some of the properties of it. And we've hit some of these before. Okay? I think. This is theorem 2.3. All right. Properties of matrix multiplication. We're starting with A, B, and C are all matrices. Now notice before when we're talking about matrix addition or subtraction or those kinds of things, all we had to say, they're the same size. They're m by n matrices. You can't say that with matrix multiplication. We say A, B, and C are matrices, but then you have to use sort of the weasel words here, and that fact they put them in parentheses, with sizes such that the given matrix products are defined. So I'm going to say with sizes appropriate, or with appropriate sizes. Okay? Now, I'll explain what that means maybe a little bit later. C is a scalar. Okay? The following are true. That's what's given. Here's what the results. If you are multiplying, I'm sorry. Okay, goodness gracious. A times the product of B and C, then that's going to equal the product of A, B times C. Time out team, okay? We've got to make sure these matrices are sized correctly. So since we're starting with A out here outside the parentheses, B, C inside, let's start sort of like the old thing goes in parentheses first. You choose a size for B. Choose a size, any size. Letters. Yeah, how about M by N? Would that be okay? Now what must be the size for C, or at least part of the size? N by something else. Let's just call that P. Okay, then the product of these two is going to be M by P. Okay, now A is going to have to be what size? Okay, yeah, let's do L because O looks too much like a 0. L can look like a 1, but if I write it script like that, it's got to be what size? L by M. It's got to be L by M. So this product has got to be then L by P. Okay? Now, we can't change them now that we've got them. Let's see what we had here. A was an L by M, and B we chose to be an M by N. Okay? If you multiply those two together, what do you get? L by N, and then multiply that by a C. Yeah, C was N by P. And sure enough, those go out, and you're left with L by P. Goodness, I can't write. Let me start again. Goodness gracious. I want to blame it on the pen, but I don't think it's the pen's fault. L by P. Okay, and sure enough. Now this doesn't say they're equal, but it at least says the sizes have to be right. And given the sizes work, yeah, we'll concede that probably that is true. And of course, this is the property of associative property of multiplication. Okay? Now, if it's okay, I think I will erase some of, well, let's see if I can get it all in. 2. Number 2 here. A times B plus C they're claiming is AB plus AC. Okay, let's use the same size as we did. No, we can't use the same size as we did before, can we? Because now that we have an addition, those two have to be the same. So what, if you choose B to be an M by N, now C has to be an M by N, right? No choice around it. The sum will be an M by N. Multiply that by an L by M, like we did before, and you get over here an L by N. Okay? Yeah, I have trouble doing that. Okay, we said this was a L by M, and this was a M by N. Then the answer is an L by N. Okay? Well, this was an L by M. Yuck. L by M times a M by N. Okay? And that came up being an L by N. And you're adding these together, so sure enough, you do get an L by N. Okay. So yeah, the sizes work, and I think we can have pretty good confidence the numbers will work as well. Okay? Now, almost the same type. And this was a distributive property of matrix multiplication over matrix addition. Okay? Now, the third one is almost the same. I'm not writing those in because they're in the book. This time we have an A plus B times a C. And the claim is that's got to be A C plus BC. Okay? Now, again, start in parentheses and name that. You want to use what we called A before, you want to use what we called B before. You've got to do one or the other. Which one do you want to do? Which? A the same or B the same? A the same. So this will be an L by M. Then B has to be L by M too. So you see they both couldn't stay the same. You add those together, you get an L by M. Oops, there I went. Need to make it script so you don't think it's a 1. And what does C have to be then? M by something. Why not N? Okay? And then that product's going to be an L by N. Okay? Well, this was an L by M. C was an M by N. And sure enough, this is an L by N. Oops. Okay. Plus, and this was a L by M times a M by N, and that gives you an L by N. Add those together, you get an L by N. So sure enough, the sizes work. I think you can be pretty confident the numbers do too. Now, is that just the same as this? No, it isn't. Okay? This you're multiplying, you're distributing from the right, there you're distributing from the left. Okay? They both work, but they're not the same things. Okay? And then the fourth one is some constant C. We finally got a constant here, times AB. They claim is going to be the same as CA times B, and that also is the same thing as A times CB. Okay? Now, it almost looks like, the first part especially looks like it is an associative property of a scalar multiplied by a product of two matrices. And that would be the scalar times the first multiplied by the second. But then the second equal sign says that's the same, not, you can't leave the order the same. Only the scalar can swap orders. The matrices can't. Okay, that is a key factor here. That A times CB. Frankly, the sizes aren't going to tell you a lot. You let A be L by M and B be M by N. This is a L by N. C times L by N is still a L by N. C by A. L by M is a L by M. Multiply that by N, M by N. You get that. And this is the L by M times M by N. You get the L by M. So yeah, the sizes work, but notice the only thing you can change the order of is the constant, the scalar. You can't change the order of the matrices. And that was something they pointed out in the side note, the margin note here. Notice there is no commutative property of matrix multiplication. And that's why all these multiplications, you keep the order as they were. You have to keep the order as they were. Okay? You can't flip-flop. Keep the order as they were. Keep the order as they were for the matrices. The scalar can move around, but the matrix can't. If it's AB, it's got to stay AB. AC, it stays AC. Okay? You can't flip-flop. Now, you can associate, but you can't exchange. You can't commute. All right. They do a little proof there. Do you think we have time for example 3? 3 minutes? What you think? We might be able to get it done. Let's go quickly. Okay, here is matrix A is 1, negative 2, 2, negative 1. Matrix B is 1, 0, 2, 3, negative 2, 1. Matrix C is negative 1, 0, 3, 1, 2, 4. Says find the product ABC. It says first multiply A by AB, then multiply by C, and then do it A times BC. So the first time we're going to multiply AB. So let's do that. 1, negative 2, 2, negative 1 times 1, 0, 2, 3, negative 2, 1. Okay, can you even multiply those two?
Yeah.
Yeah. 2 by 2 by 2 by 3, what answer will you get? 2 by 3. So let's write down 1, 2, 3, 1, 2, 3. That first entry, what do we get? 1. Second?
0.
You do first row by first column. No, that's the 1, 1 entry, right?
Yeah.
So that would be
1. Negative 6.
is
Negative 5.
-5. Okay. I think you're right. We're going to have to start that next time. You got
You
to.
said to get the first row, you do the first row in the first column.
Okay. To do the 1, 1 entry here, you determine this is a 2 by 2 by 2 by 3. The 2's cancel out. Your answer is going to be 2 by 3. So write your 2 by 3 here and put blanks in it. Okay. This is the 1, 1 entry. To get the 1, 1 entry, first row by first column. Do the 1, 2 entry, first row by second column. So you do. Yeah. Okay. We'll come back and we'll pick up there next time. I thought maybe we could zap it out, but nah, that was unrealistic. Okay. All right. Let me give you a few homework exercises in this section. I don't know where my sheet has gone, but okay, we didn't get too far, but we got some started. You can do any of the odds 1 through 5, any of the odds 7 through 11. You can do number 13. That's one very similar to one we did in the text. We only did one in the text. This has 4 options on it. Think you can start doing any of the odds 15 through 19. Okay? And I think you can do 21. Well, we were just starting to do that, so you can hold off 21 for now if you want to. We'll do that starting next time. All right, good deal. Any questions? All right. Good deal. That means have a good weekend. Of course, making it good, we'll be working on plenty of linear algebra, right? All right. Hey.